My name's Mitch Hammond. Math 1C, De Anza College. This is my project 2 about vector fields. So I decided to do my project about game design because vectors play an important role in like game mechanics and whatnot. I know it's not like real life application, but you have like a lot of designers in the world who are constantly working on games, and millions of people play those games. So the vectors in the games do end up affecting a lot of people. So I guess it still is real life. Aspect of vectors in games that I want to talk about is gravity and how gravity works and functions in games through vectors. So say you were to jump in the air, like you went straight up, you would come back down, right? That's gravity. That's how gravity works. Now, if I were to get a running start and then jump, I would thrust myself and go outward while also going up, but I would still come down because of gravity. So games have to worry about this mechanic too because they want their games to be realistic, the game designers and whatnot. So we do this through vectors. The jumping mechanic in games, there are three important vectors. First one is gravity, the next one is thrust, and the next one is the addition of both gravity and thrust. So a gravity vector in a game is a line straight down. A thrust vector is a line going sort of angled up like this. So if you imagine a xy plane, you'll have the gravity vector will go straight down. So the x value will be 0, the z value will be 0, but the y value will be some negative amount. It depends on the game and how much gravity you have involved. So the thrust value will be an xy value in the quadrant 1, and it'll be even. So maybe like, I don't know, some arbitrary number like 5 and 3. And what you'll do is you'll then take the gravity vector and add it with the thrust vector, and you'll get a new vector. And basically what that vector is sort of how the jump mechanic works. It'll be show like where the peak of the jump is when you combine the thrust and the gravity, and I'll show a graph about that right now. Example of the thrust and gravity sort of working together to create the jump mechanic. So I've created two vectors. They're pretty arbitrary, but you get the point. So the thrust vector is the red line, and its values are 3, 7, and 0. And the gravity vector is the shield line right here. As you can see, it's 0, -5, 0. And what happens is we add those two together. So that's right there. That's the blue line. So we do 0 plus 3, -5 plus 7, and then we leave the z value as 0 because we're just doing a basic example of how thrust and gravity work together to create a jump mechanic. And this will sort of be the peak of the jump, and then over time you'll go down because that's how gravity works. There's another complicated formula for creating the whole entire motion of a jump, and I'll show you that right now. So this is just a little screenshot from a video talking about jumping and gravity inside of games. So if you look at the game loop right below, so you have M prime and V prime. So M prime is just Mario's position on the screen, and so as he goes up, he's going to end up coming down. These are the functions for how he'll come down. So the V vector is going to represent thrust, and then the G vector is going to represent gravity. So as you can see, and then delta t is just time. So over time, as more time passes, the gravity vector is going to get bigger, which will decrease the size in the velocity or the thrust vector. So as time goes on, the thrust vector will get smaller, and he'll come down to earth after he peaks at his jump. And so the next vector concept we'll discuss inside of games is the cross product and how it works inside of game mechanics. And you run into a wall like this. So instead of bouncing off the wall like this, or just sort of running into the wall and then being stuck on the wall, you want to run into the wall like this and then slide across it and just move across with the wall, straight down the wall. Well, that's where the cross product comes in with. Is going to represent sort of like moving from one vector to another vector and be that point where you've gone from one path and run into another one. And I'm about to show you a graph that'll explain that much better. So this graph kind of shows how the collision mechanics works in games. Sorry, the graph doesn't look great, but I'll try my best to explain. So the blue line is a vector starting at the origin going out. Its values are 2, 4, and 3, and the yellow line sort of represents the collision. So when the blue line hits the yellow line, we get a new vector, 3, 1, 0, and as like if you were playing a game, you would go down the blue line, run into the yellow line, and then you would go along the wall of the yellow line. And the black line represents the cross product, which is -3, 9, -10. And so what that does is for the like game engine, it'll represent like a perpendicular point, like where the player is hit, and then it'll change the mechanics. So now instead of like walking down a path or something, you'll be walking along a wall. So you have boundaries inside of your game, and the player can't just like fly off the screen or whatever. Similar to how gravity doesn't let the player just bounce around and stuff. This stops the player from like leaving certain areas and doing all that. And it's found with the cross product. So the cross product will be the perpendicular point where the vectors have changed. Okay, so the next aspect of vectors in games that I want to talk about is the dot product and how the dot product can be used in video games. Dot products in video games to find like a player's viewpoint. So, you know, I have two eyes, I have peripheral vision. So if I look like straight on, I can kind of see like that. So the games try to emulate that too, especially in first person, like 3D open world games. So what they'll do is they'll take two vectors, have them go outward. So say my eyes, or I guess my nose would be the origin, and the two vectors will go out like this. And what we would do is we would take those two vectors and figure out the angle between them. And I'll show a graph to explain that much better. And here's a graph to sort of explain what I was trying to say earlier. Once again, very sorry, bad at using the software. So we have two vectors, both starting at the origin. Vector 1 is 2, 5, 6, and vector 2 is 4, 6, 1. So as you can see, they're sort of going in two completely different directions. So if we sort of visualize that as the player's eyesight in a first player game, we can figure out the angle between them and sort of understand how much the player is able to see as they turn. And we can do that through using cosine theta equals the vector A times vector B, and then dividing that by the magnitude of vector A times the magnitude of vector V. And I've gone ahead and done it with these two vectors right here. And the answer I got was the angle of the two vectors in between it was 41 degrees. So the player would sort of have like the viewpoint of 41 degrees and they would be able to see anything in between the two vectors. Learned how vectors are used inside of game mechanics and game engines, whether it's through jump mechanics with gravity and thrust, or it's through collisions into walls and changing your direction using cross product to change the direction of the player, or how the two vectors of sight have a certain angle, and that's what the player is able to see. That's what all the other creatures and whatnot in the game are able to see. So I'm not like great with vectors and I'm not great with game design, but I'm trying my best to explain it. So now I'm going to show you a video of a game that I think very well emulates all these factors of vectors, and here we go. So someone just playing Minecraft and running around a Minecraft world. So Minecraft is an open world sandbox game, and what it does is it generates random terrains with these blocks. And what's interesting about Minecraft is it actually uses sort of like a vector plane, if you will. So if you look up in the corner of this video, it says position. So that's his X, Y, and Z values on the screen right there. And as you can see, as he moves around, he's changing his position on sort of the vector plane. And we can see when he walks off a little like jump, if he's one block higher than the next block and he walks off it, the gravity will take him down. He's not able to like fall through blocks, and that's due to the collision mechanic that I explained before. And his sight is based on the angles, which I also explained, and this is pretty much all of that at work altogether.